Hey everyone, today I'm going to be explaining how I built this program in Python which can predict the emotional state of a subject given their EEG readings while watching various movie scenes using a recurrent neural network in TensorFlow. So first off, we're going to be importing the libraries that we're going to be using for this program. So we have NumPy and Pandas, which are basically used for data manipulation and data handling. And then we have Matplotlib and Seaborn, which are used for data visualization. And this just makes it easier for us to understand the data and know what we're working with. And then finally, we have TensorFlow and these functions that we're going to be importing from sklearn, such as train test split, confusion matrix, and classification report. And this is what will help us for the machine learning itself. So if we have a look at the data here, you can see that there's quite a bit. And so if you look at the very last column, which is the label column, we can see the values neutral, negative, and positive. And what these represent are the emotional states of the subject while watching these various movie scenes. And so this is what we'll be trying to predict with our recurrent neural network. And so now we have the value counts. This is used to look at the class distribution of our label, and we do this to ensure that there isn't an imbalance in the amount of classes represented in the data, which can really affect the training of our neural network, and as you can see, they are fairly balanced. And so next up, we have the preprocessing function. This is where we prepare the data for it to be passed through our neural network. So from the data, you may remember that in the label column, we had the values negative, neutral, and positive. And this is what we call categorical data. So what we have to do is enumerate each of the values so that the computer is able to understand it. And so what this line does here is it takes each of the values from the label column and replaces it with a number using the dictionary from up here. So essentially every negative will be replaced with a 0, and every neutral will be replaced with a 1, and every positive will be replaced with a 2. Because it's the label column that we're trying to predict with our neural network, we're going to be detaching the label column from the rest of our data. So then after that's done, we split the data into training and testing groups, with the training group consisting of 70% of all the data. And so when you use this train test split function to split the data into training and testing groups, it automatically shuffles the data for you. So we set a random state here just to ensure that the data is being shuffled the exact same way every time we run this. And once we pass the data through the preprocessing function, our data is ready to be used. So if we take a look at our training data and look at the index, you can see that it's been shuffled, and all the way towards the end, you can see that the label column has been detached, which is being stored in ytrain. And so here comes the part where we model our neural network. We're going to be using a recurrent neural network because the data that we have is a time series data, which is data over a period of time. So what RNNs do is that they pass the data portion by portion, and as each portion is being passed, it also takes into account the last portion it saw. And it's important that we use a recurrent neural network because the values in the data aren't necessarily independent, but rather tied in with previous and following values. And so that's why we use an RNN instead of a regular neural network. So instead of using dense layers as you would in a regular neural network, we're going to use a gated recurrent unit, or GRU, which is quite similar to an LSTM in the way that it follows the same concept, except that it's a bit simpler. So we're going to use 256 units, and then we're going to have return sequences turned on. And because return sequences is turned on, and because of the way that it works, it will basically give us more data in the form of a two-dimensional array. And this often improves performance because obviously there's more data. However, because now it's outputting more data in a two-dimensional array, we're going to have to flatten it from a two-dimensional array into just a long one-dimensional vector. And so then we're going to pass the output from the GRU to flatten, and then the output from flatten into the output layer. And then there's one more thing I need to mention, is that the GRU layer requires the input to be three-dimensional, and the reason for that is because often each bit of data that comes in is encoded as a vector itself, so it needs a third dimension. So to compensate for that, we're going to get an expand dims layer, which takes the inputs here and expands the dimensions along the axes too, which gives it its third dimension. And so this expand dims layer will be passed into the GRU. And so here we compile the model using an atom optimizer, and we use a sparse categorical cosentropy, which is best suited for multi-classification problems like the one we have right here. And once we train the model, we store its result in history. So we're going to pass through X train and Y train with a validation split of 20% and a batch size of 32, which is the number of samples to work through before updating the internal model parameters, and 50 epochs, which is the number of times the entire training dataset will be passed through the model. We won't actually be needing these many epochs because we'll be employing the early stopping callback. This will allow the model to take a look at the validation loss after each epoch, and it will evaluate if the loss is improving. And if it doesn't improve for a specified amount of epochs, which we've specified as 5 here, then it will stop the training and restore the weights from the best epoch. And then to top it all off, we can have a look at the results our model produced with a 93.3% testing accuracy, and also have a look at the confusion matrix and classification report. So just to explain the confusion matrix, it basically shows how many times each class was predicted and how many of them were correct. So as you can see here, negative was predicted a total of 181 times, and out of that, it correctly predicted 173 times, and it falsely predicted positive 8 times. And with that, we'll conclude today's video. Thank you guys so much for watching. I hope you all enjoyed, and I'll see you guys next time.